Swayam Prabha. Digital India. Educated India.
So I want to continue what we started yesterday about elasticity, and now I want to introduce eigenstrains and how we can both measure them in an atomistic simulation and how we can use them to model dislocation defects and the interactions between the defects. So to set the stage, let's assume that, so I have we're going to look at an alloy with a precipitate. So I have an alloy and so my alloy, I will assume that it is a continuous elastic medium with linear isotropic elastic properties, right? So exactly like what we did yesterday. So elastic isotropic medium. And now let's assume that behind this elastic isotropic medium, there's a lattice with a lattice parameter here that I will call A. Now in this lattice, I am going to assume that there's a precipitate that forms, but the precipitate is made of a second phase that does, I mean, in generality, it does not have the same lattice parameter as the matrix. So here I have a second phase, and in that phase, again, I'm going to assume that this is an elastic isotropic medium, but that behind this elastic medium, there's a crystal with a lattice parameter A prime, right? So it means that this medium here, when it is at rest, meaning that when there is no stresses inside this medium, the lattice parameter wants to be A prime, whereas in the matrix, the lattice parameter wants to be A. So what does it mean in terms of elasticity? I need to take a reference configuration. So that would be my reference configuration. And now it means that at rest, or when there is no elastic stress in the system, in the region which is inside the precipitate, actually the system wants to be deformed. It wants to have an A prime lattice parameter instead of A. So it means that actually here at rest, the system wants to have a deformation which will be A prime minus A divided by, so again, it's the relative displacement. So I go from A prime to A and I divide by the reference lattice parameter, which is A. Do you see what I mean? I'm not sure. And so we've seen yesterday that deformations are tensors. So actually, if the only difference between the two materials is a difference of lattice parameters, it means that actually this region here wants to be either purely contracted or dilated, depending on the sign. And so this means that actually the deformation, because it's a pure traction or compression, would be something like this. Yes? So, yeah, and so usually the usual notation is that this deformation, we put a star to say that it's not an actual deformation of the system. It's where this region wants to be, and that is called an eigenstrain, or we also call it a stress-free strain. Because now if I put both together, so I have my matrix and I have the solid, the precipitate inside. If I am here if there's no stress, the system here wants to have no strain because we took the matrix as the reference. Whereas, so here I have the stress. So in terms of tensors, the stress will be the elastic constants times the strain or the deformation tensor, with the deformation tensor defined as before as from the displacement, dui dxj plus duj dxi. But when I am here, the system to have zero stress, it wants to have a deformation which is equal to this eigenstrain. So actually in this region, what I have is the stress will be the same stress tensor, the same elastic constants, but now I have to dot it with what? With the current deformation minus the deformation it wants to have, so the eigenstrain. You see what I mean? So when I am inside the precipitate, actually to be at equilibrium or to be at zero stress, and that's why it's called the stress-free strain, to be at zero stress, the strain has to be equal to epsilon star, to the eigenstrain, such that the lattice parameter here will be equal to A prime instead of A as it is outside. Am I making sense or not? Yeah, exactly. To bring the system inside the precipitate at zero stress, you need to have a deformation inside that takes the A lattice parameter to A prime. So you need to have a finite deformation to be at zero stress. So the reference state here is the matrix itself. The reference state here is the matrix deformed by epsilon prime to go from A prime to A. Does that make sense or not? We assume here we have just a difference. So yesterday, for those who were at my talk, that's what we call the misfit volume, or it's related to a misfit volume. So it's just a difference in lattice parameters, and it's an isotropic deformation to go from one lattice parameter to the rest, to the other lattice parameter. So it's called we call that usually a misfit volume because it's just a change of volume. So for now. Not necessarily. No, it's not at the same stress. For now, I'm just saying that the definition of the stress at that point will be this, and at that point, it will be that. I'm not yet saying, and we're gonna write it right after. I'm just saying in this region, the stress will be defined like this, whereas in this region, the stress will be defined like that. For now, there's no mechanical equilibrium. It's just a definition of what is the stress in the different regions. What is the stress at equilibrium? So now, this is just the definition of the stress. Now, when I put this precipitate with an A prime parameter inside this matrix with an A parameter, clearly the deformation will not be exactly A here and A prime, or here. The lattice parameter will not be exactly A here and A prime there, right? That's not possible. The lattice parameter will gradually change from one to the other. So the stress inside the precipitate will not be exactly equal to zero. And the stress outside also will not be exactly equal to zero. How do I determine the stress at mechanical equilibrium? So I don't necessarily need to apply forces on the outside for now. I can have a mechanical equilibrium with forces on the outside or without, with periodic boundary conditions or fixed boundary conditions. For now, we don't need to specify that. But we've seen yesterday. What we showed yesterday is that mechanical equilibrium implies that I have the divergence of the stress tensor plus body forces is equal to 0. Yes? So now what I can do, so actually what I can define is, I'm not completely organized. What I can we have that, and what we can do is we can define generally sigma as the stress tensor, the elastic constants. double contracted with epsilon minus epsilon star with epsilon star. So this is a function of space, and it is equal to 0 in the matrix. And it is equal to A prime minus A over A times the identity matrix inside the precipitate. Yes, so by taking the eigenstrain equal to 0 outside and equal to its value inside, then I have a single definition of the stress, which is this. Outside, this term is 0, and I get just C times epsilon. Inside, I have C times epsilon minus epsilon star. Yes? I take that, and I put it in here. What happens? So I have so the divergence is, it's a linear operator. So here I have the divergence of C epsilon minus C epsilon star. So this, using the linearity, this becomes divergence of C epsilon minus divergence of C epsilon star, right? So I have divergence of C epsilon minus divergence of C epsilon star plus plus the body force is equal to 0. Or, without eigenstrains, what did we say? The equilibrium was, so so the equilibrium was what? Yesterday it was just divergence of sigma, so it would be divergence of C epsilon plus a body force is equal to 0. What does that mean for this eigenstrain? It means that the eigenstrain acts as a body force inside the material, right? So actually I can solve for the equilibrium of that configuration as if there was no eigenstrain, but by replacing the eigenstrain by a body force inside the material, a body force which is 0 when I am outside and which has some value when I am inside. And so I can use the tools that we haven't really talked about yesterday, but I can use the usual tools to solve for the elastic equilibrium, but now including the eigenstrains, and so modeling the presence of a precipitate inside the matrix. Do you see what I mean? So just to give you, I won't go into too much details. The math are a bit involved, but I want to go back to the Green's function that we haven't really talked yesterday, because to solve this equation in a closed form, we need to use Green's function, and actually we need to go to Fourier space. So bear with me. I'll try to tell you how it works, at least in the big lines, and then we'll see. So if I expand that function, what does it say? So I have the divergence, and what is this double contraction? What does it give me? Second order tensor, and how is the tensor, or if I look at the, so I have C, if I look at the epsilon, if I look at the ij component of this tensor, how is it expressed? So there's a C ijkl, epsilon kl, right? And what is epsilon kl? What's the definition of epsilon kl in terms of displacement field? So there's a 1/2 here, and there's a duk dxl plus dul dx k. So now this, I can write it 1/2 of Cijkl duk dxl plus 1/2 Cijkl. Do you know the Einstein convention, summation? So here, for example, the k and l are given twice, so it means that they are summed, right? Otherwise, so normally I should write a sum here over k and l, right? If you're okay with it, I remove that, and we accept that indices that are repeated are summed. Is it how you say in English? Yeah. So this would be a sum over KAL and these terms, right? And I have a CIJKL DUL over DXK. Now, what have we seen yesterday? CIJKL is also equal to CIJLK, right? So this is CIJLK DUL over DXK. And now L and K's are just names. If I call L K and I call KL, if I reverse the name of the indices, I go back to exactly this term. So these two terms are equal, right? And so the half disappears, and this is CIJKL DUK over DXL. Now, if I take the divergence of this, because I have the divergence here. So what will be the divergence of this term? So if I write a divergence of C epsilon, and this is a vector, right? So I have a component I. By definition, what is this? So this is still a matrix, right? It's a matrix with indices I and j. And the other indices are summed. Now, what is the divergence of that matrix? What did we say yesterday? The eth component of the divergence of a matrix is? Yeah, it's the divergence of the eth line of the matrix. So that would be, if I take the divergence here, so I would take the divergence of the eth line, so I will not change. But now to take the divergence, I have to do sum over j of the derivative of the j term by xj. So it's going to be, and this is a constant, CIJKL. So this is CIJKL, and then I have d2uk over dxj dxl. You agree with that? Yes? So what you have, so in the end, if I rewrite this equation, I have sum over j of CIJKL d2uk over dxj dxl, which is equal to some function, some volumic function f tilde, for example, where f tilde is or minus f tilde, where f tilde is the real volumic function minus the eigenstrain term. And here I have the index I, so actually I no longer have the vector. This is the volumic force along direction I. So epsilon star will see, yeah, that epsilon star will depend on the defect we are looking at. So if it is a precipitate of a second phase, epsilon star will depend on the lattice parameter of that phase. So that's given in the problem. We don't have, this is a constant, we don't have to worry about that value. Is it okay for more or less for everyone? Because now the next step is to go to Fourier space. So how do we go to Fourier space? What we're gonna say is that the component uk here of the displacement vector is equal to the integral of capital K, which will be a function of wave vectors, exponential minus I Q R dV over the volume of my system. Are you familiar with Fourier transforms? Does what I write here, does it make sense or not for you guys? Yes? Yes? No? Maybe? Right, so here I have a function of R that I replace by a function of wave vectors by taking the Fourier transform. So I have this function of the wave vector, and then I multiply by the exponential minus IQR. And the dv would be the same as dr. Like this. This is a function of R. Oh, sorry. Yeah. You're right. Thank you. yeah. Good catch. Thank you. dq. Sorry, it's not a dv. And so this is not v. This is in Fourier space. Yeah. In Q space. Does that make sense a little bit? Yes, for some of you at least. Yes. Now the good thing about that is that what I want to do is I want to take the second derivative of u with respect to xj and xk. What happens if I do that? If I take this function here and I take the derivative with respect to xj, for example. Because this qr, this is q1 x1 plus q2 x2 plus q3 x3. So if I take a derivative with respect to one of the coordinates, I have a minus iqj, for example, which will go down. If I take the second derivative with respect to xl, I'm going to have another. So this is going to be duk over dxj dxl. This is minus iqj minus iql. And then I have the same function here. And this does not, this is dependent on k. So this is like this. And then I have uk of q exponential minus I qr dq. Yeah? So the minuses go. This is I squared, so I have a minus outside here. And then the i's are gone. What does it mean? It means that the Fourier transform of the second derivative of u is just qj, ql, and the Fourier transform of u. So here, this will become sum. So I can. This is linear, so I can put it inside the integral. So I have a minus integral. I have sum over j of Cij kl, qj ql u of q, Cij kl. Yes. And then I can also take the Fourier transform of this term here. If I put it back, I have a plus, and I have an f of fi of q. And this whole thing is exponential minus iqr dq. And this is 0. Right? And so this would be the Fourier transform of the volumic force that may or may not include some eigenstrings. So now for those who, so the minus should be inside. For those who know a bit of Fourier transforms, if the Fourier transform of this function is equal to 0, what does it mean? This is only possible if it's not. I'm not sure that's not. So I mean, you can show that if the Fourier transform of a function is 0, it means that the function itself has to be 0. In other words, the exponential here forms the basis of function, and so as a function of as a basis of functions, if I have a function which is equal to 0, all its components, so these guys here, have to be 0. So actually, mechanical equilibrium in Fourier space boils down to sum over j ofCijkl qjql uk of q is equal to minus the Fourier transform of the body force in q. Yes? Now, what we want to find is this guy, right? If we know the Fourier transform of the displacement, then we go back to, we invert that relation, we go back to real space. So I've put, so if we know the Fourier transform of the displacement, then we can go back to real space. Once we know the displacement in real space, we know the strains, the stresses, we know everything, right? So, and what is the form of that equation? If I am looking, so here, if I put all the summations, there's a sum over J, over K, and over L. So what is, yeah, so here, if I look at, if I take the sum over K outside here, and so I have if I have the sum over K and I have a UK, and what is this? How many indices? So here I'm summing over J and L. I have J and L here, and I have J and L here. So I have two indices that remain, right? So I can call that, for example, a J of I and K. And so the equation is sum over K of JIK UK is equal to Fi. What's the solution of that equation? Formal solution? Or what's the shape of that equation? If I write it in terms of vectors and matrices, this is the matrix J times the vector U, which is equal to the vector F. So U is equal to J minus 1 times F. Okay, I think you have suffered enough. This would be, this J here is what we call it's the Green's function in Fourier space. And so you have a general solution here by inverting the Green's function in Fourier space. Once you know this term, and this term here depends only on the elastic constant of the medium and on the wave vectors. So you invert, you multiply by whatever volumic force you have, and you have directly the solution of the displacement field in Fourier space. And then you can go back to real space if you want to. So this is a function of Q. Everything is a function of Q. If we put back this guy here, you see, if I have I have a cell and I assume that I have a precipitate, or I don't need to know it's a precipitate. I take a simulation and I know that in the simulation there is some eigenstrain that depends on space. Right? I know the eigenstrain field in real space. I can compute this term, take the divergence, go to Fourier space. Now I know the Fourier transform of the eigenstrain field with the elastic constants here. I multiply that by the inverse of the Green's function. I get the displacements, and then I can come back to real space. This is phase field simulations. The phase field simulations that include elasticity, it's exactly what they are doing. Nothing more, nothing less. They are just solving this equation. Actually, they only go back to real space to make pretty pictures. But otherwise, everything is, because you never really need to go back to real space. Phase field simulations, so I have examples. I'll go back to the slides to make sure that we have all the details, but I'm sure you have all seen this type of phase field simulations where you have precipitations, and because of the elastic interactions between the precipitates and the matrix, you can form anisotropic microstructures. What they are doing here is nothing more than what we have just said there. This is at the microscopic scale. So this is not atoms, these are continuous fields. There's just one thing that they have to add. It's to stabilize the interfaces. There's an extra term to account for the energy of the interface. But that's it. The rest, for the elastic part, they just back in the days, I wrote a code that implements that. It's not just that. It's a bit. It takes care, but the machinery behind it is just that. Is you compute the inverse of the Green's function once and for all. You take the Fourier transform of your eigenfield. You get the displacement. You get there, and then you can have evolution equations for the eigenstrain field, and that gives you the evolution of the microstructure that you have here. That includes elasticity. So the evolution, so you start here with an basically with circular precipitates, and they become elongated because of the elastic cost. So the eigenstrain inside these precipitates is not just volume change. There's a tetragonality. We're going to talk about it later on. But the eigenstrain is not just a change of lattice parameter. It's a bit more complicated, and so you have regions where the elastic interactions are weaker than other regions, and that breaks the symmetry of the precipitates and gives you these elongated precipitates. Do I make sense? Yeah. So you see, you suffered, but now you know what is behind these phase field simulations. So just to go back to the slides, first I want to acknowledge. So the two Bibles in this field are the book by Toshio Mura on micromechanics of defects, and then all the work done by Armen Kachaturian, and in particular his book here, A Theory of Structural Transformations. They both, basically, they do exactly the same. They don't necessarily explain the same way, but the basis is the same, and everything is based on eigenstrains. So what did we say? We said, let's consider a precipitate in a matrix. The lattice parameter in the precipitate A prime is different from the lattice parameter in the matrix. So it means that if we take the matrix as a reference, the medium inside the precipitate is at minimum energy if it is trained by this eigenstrain tensor that we have talked about. And so it means that now the elastic deformation is the difference between the actual deformation and the stress-free strain, and the stress is the difference between the two terms. Mechanical equilibrium is given by the divergence, and then we do. Sorry? Between the precipitate and the matrix? Yeah, so that's one caveat. If I want to do these calculations analytically, I have to assume that the elastic constants in the precipitates and in the matrix are the same. You can extend these calculations with elastic constants that depend where you are, or the elastic constant can depend on the stress-free strain itself. But then the calculations, you cannot have a closed form solution like this one. You have to do a self-consistent loop calculation to find the equilibrium. So you can do it, but in many of the phase field simulations, they just assume homogeneous elastic constants. So you have to look at the paper and what they have done. If they tell you that they have accounted for inhomogeneity in the elastic constants or not, in many cases they don't, so that they can use this simple relation. That's the main limitation of what is done here, in my opinion. For now, as the illustration here, I've assumed that the eigenstrain is diagonal. But you see, in what I've written, I've never used that hypothesis. So that equation here applies whether the eigenstrain is isotropic or not. Yes? Yeah, I'm gonna illustrate it just later on. So body forces. Then we suffered through the Fourier transform, and we get this expression, which hopefully is the same as the one I wrote here. And so this is so elasticity in Fourier space using eigenstrains is usually called microelasticity theory. And that's what is in Miura and Khachatorian's book. And this is what is used for the phase field simulations of the microstructure evolution. And as we just said, the important limitation is that for the simple, and so in that case, for example, I think it's the same elastic constants. They assume that, but that's the main limitation. Matrix and precipitates must have the same elastic constants. So typically, so what you do is, we have seen that the elastic energy is 1/2 of the integral of the stress contracted with, so you have epsilon minus epsilon star dV, right? So and C is itself sigma is itself C double contracted with this guy, right? So you see now if you compute this energy at equilibrium, this term and that term, the stress and the strain will themselves become functions of epsilon star. Yes, so when you solve for the equilibrium here, this will be a function of epsilon star. So the displacement becomes, once you have applied equilibrium, the displacement become themselves functions of epsilon star. So everything is a function of epsilon star. So this whole thing here, this becomes a function of epsilon star. Right? Now you can take a derivative of that function with respect to the different terms. And that will give you a driving force. And that's what is implemented in here. Or rather, so what I'm saying is not true. So this is a functional function of epsilon star of which depends on r. And so actually, then you get a local force by looking at how much the energy will vary as a function of epsilon star of r. Yeah, and that gives you the driving force for the value of the eigenstrain at that position in space. And that's what is in there. It can be a bit, so yeah, there are some things that we should add. So for example, if it is the precipitation of a second phase, the concentration of the second phase has to be constant. So once you have the driving force, you have to make sure that in the evolution, the overall concentration of the solutes will not change. So there are some details here where you have to be a bit careful. But I don't want to go into this. Again, I could spend a whole week talking about that. Do you have at least a feeling for what we said? Yes, even if maybe all the mathematical details are not entirely clear. So now.
We are assuming that only precipitate is getting strained and not the matrix.
So in the end, when you solve for the elasticity, the displacement will be non-zero inside the precipitate, but also outside the precipitate. And it will vary. So if I have a big enough cell and I have a precipitate, the displacement will be zero far away, and then it will go down. It will be close to A prime, so close to A minus A prime inside, and then it will go back further away. So yeah, displacements will be, it's beautiful. I mean, I really like that framework. So by this integration here, what you're going to get automatically continuous displacements. There will be no discontinuity. Continuous displacements that will vary in space to try and accommodate as much as elasticity allows you for the difference in lattice parameter inside and outside.
For this continuous change, does the precipitates have to be coherent?
Yes. This I could have put that as another limitation. Yes. because we assume continuity of the mechanical properties at the interface, implicitly we assume that it's a coherent interface. Yes. Yeah, good point. Are there other questions at that point? So what I wanted to say is, where is it? It's here. So no more math for some time. Not that long. There's more math coming up, but so here we said, several of you pointed it. We looked at an eigenstrain tensor, which is proportional to the identity matrix. And here we have A prime minus A, blah, blah, blah. That would be a delta V over 3V. That is what in the community we call the misfit volume between the precipitate and the matrix. Right? But as you all said, it does not need to be an identity. So imagine, for example, that we are looking at a phase transformation from a cubic phase to a tetragonal phase. So initially I have A, and I have a transformation to something that has here an A prime, and now I have a B prime here, and I could have a third dimension. What will the eigenstrain look like in this simple case? So here the eigenstrain will be something, there will be a value here, epsilon 1, and then I have an epsilon 2, and then maybe an epsilon 3, right? There's more than that actually, and that's why it's called also phase field simulations, because this is, yeah. If I start from a square or a cubic cell like this, and I do a tetragonal deformation like that, is this the only solution, the only possibility? I'm not sure I'm clear when I'm asking that. Here I've assumed that in the transformation, this side here gets bigger, and this one may be bigger or smaller. But something else could have happened. I could have another variant where it's the same, but now B prime is here and A prime is there. So here you would have, in these simulations, very often, you have several fields that can depend on the variant that you have. So that would be a variant 1, and then you could have a variant 2. That would be epsilon 2, epsilon 1, epsilon 3, etc., etc. This is what you have to do when you break symmetry, and then you have different populations depending on the different variants that you have. But this is directly also can be directly included in what we have said. So if we go back to our our business in metals and ceramics. What kind of crystal? So we have talked about crystalline defects, 1D, 0D, 1D, 2D, 3D defects. What kind of defects do you think you could model elastically by using that kind of eigenstrain matrix? Sorry. Yeah. Okay. Sorry. Yeah. So precipitates, but is that it? It's the only defects that you can model with a simple misfit volume like this? A vacancy, right? A vacancy is just a very, from an elasticity point of view, a vacancy is just a very small precipitate with a smaller, or you can model a vacancy as a atomic scale precipitate with a smaller lattice parameter than the outside. What else?
So other zero-dimensional also for interstitials.
Interstitials. So you can model interstitials with that if the interstitial. Yes, but also some of you in day one you have modeled an interstitial in a FCC crystal?
Self-interstitial.
Self-interstitial, but what happens with the interstitial in the FCC crystal? Have some of you modeled the interstitial in the FCC crystal, or no one? What did we say in the FCC crystal? Because it's a very compact structure, there's not enough room to place one atom between the others, and so it takes a dumbbell, right? So if I have a dumbbell, what happens to if I want to model a dumbbell with an eigenstrain, what do you think happens to the eigenstrain matrix? Because the dumbbell has an orientation, right? The two atoms are in a given orientation. So it means that the eigenstrain tensor will look like the tetragonal eigenstrain that we wrote. If I have my matrix and I have here a dumbbell like this, then this direction will not be equivalent to that direction. So I can expect an eigenstrain for a dumbbell. That would be, as we have written, there will be an A1, and then an A2, an epsilon 1, and then epsilon 2, epsilon 2. You see, because here there's a symmetry which is broken. That direction is not the same as that one or that one. Yeah, so you have to be careful with for the interstitials. There's a third. It's not really a defect, but it's what I talked about yesterday at the seminar. The third thing that you can model with a misfit volume, a substitutional solute. Substitutional solutes, you can model them with this kind of eigenstrain. That's everything I talked about yesterday afternoon in the second part of the talk. That's how we modeled a random alloy. The best thing to do is like for a vacancy, so you cannot really take it to zero. The best thing to do is, and we're going to see afterwards, you assume that there is an eigenstrain inside your void, and then you use an atomic scale simulation to tell you, because we're going to see that we can measure eigenstrains using atomistic simulations. The atomistic simulation will tell you what is the eigenstrain equivalent to a void. It may not be as if it was exactly zero inside. You see what I mean? Yeah. It's not exactly zero inside. And for example, for a vacancy, we'll see the eigenstrain for a vacancy is not like it's a zero inside and A outside. It's in between the two. So what did we say yesterday? So we said that a dislocation is the border of a slipped region, right? So this is seen in perspective. To form a dislocation, what do I do? For example, in a crystal, I have here, I have a platelet. The height of the platelet will be the interatomic distance. And then what I say to create a dislocation, I say that this face here is displaced by the Burger's vector with respect to that one. So there's B here. In terms of eigenstrains, what do you think? Does someone intuitively have an? If I say that I have that the dislocation is actually it's a precipitate, but it's a platelet precipitate. So I have the matrix which is here, and I have the inside of the precipitate which would be here. What is the eigenstrain inside that platelet precipitate that would be equivalent to a dislocation? So what would be, so imagine I have, if I take something simple here, I have a X axis in this direction, I have a Z axis in this direction, I have a, no, it's on the other side, I have a Y axis towards the back, right? I have this platelet. The material inside that platelet, what does it want to do? at stress-free, when it is stress-free? What does it want to do? It wants to have a shift of B from one side to the other of the platelet. What kind of deformation is that? It's a shear, right? So if I'm using these axes here, and I assume that B is in that XZ plane, which component of the deformation tensor would correspond to that shear? It's XZ, right? So it would be this term here, and by symmetry we also have that term there. What will this term be equal to? What shear would that be? So it will be a shear deformation, but what's the shear deformation? It's the relative displacement. So you move by B over a distance D. So this is B over D. And because of the symmetry business, there's a 1/2. And then you have a 1/2 here, and you have a B over D here. Yes? You see what I mean? So actually, this has been done. You can model dislocations in phase field by assuming that the dislocations are platelets. And inside the platelet, you have an stress field, an eigenstrain field, sorry, which is exactly like, I mean, in this frame of reference, the eigenstrain field would be this inside the platelet and 0 outside. Now, since there we want to do, or for calculations, we want to take the limit, this, in a very general sense, you can rewrite the eigenstrain of a dislocation as, so here, if I'm turning in this direction, I have a normal n, which would be like this, and I can rewrite the eigenstrain as B, and then there's the, I never know how to call it, in French, with dyadic, you say? Dyadic product? Okay, dyadic product with the normal. And then there's a Dirac function for R that belongs to the cut surface. So, because if I take in the continuum limit, I will take D going to 0. So here I will have a divergence. I will have a 1 over D that will go to infinity, and that 1 over D going to infinity inside the platelet, and which remains 0 outside. This becomes, this is equivalent to a Dirac function, a delta of R belonging to S. So delta is equal to 0 if R is not in S, and it's infinity inside S, such that the integral gives you 1. And this B dyadic product with N is a general formula that will work in for any orientation of the dislocation, right? And this is so for those who don't know, so this matrix B dyadic N. So this is a matrix, and its ij component is just the ith component of B multiplied by the jth component of N. And I can tell you that starting from this definition of the eigenstrain and using what I erased here, you are back to exactly the same elasticity theory of dislocations as is in Herthenlothe, or what we discussed yesterday. Yesterday we said to find the stress field of a dislocation, we solve the elastic problem of a displacement discontinuity along a surface. Actually, it's completely equivalent to saying I'm going to use the framework of microelasticity theory, assuming that I have a surface with that eigenstrain. Both are completely equivalent. So we said vacancies, interstitial solutes, they can be modeled by spherical inclusions. Dislocation loops, they become a surface or a platelet of 0 width with this eigenstrain, as we said. Now, around the dislocation, you have the dislocation core here. right? That there is this region here. Now, for those who were at my seminar yesterday, I said that BCC metals are known for their non-Schmidt effects, right? And so those who are working on BCC, you know that. What we have shown in a series of papers is that actually we can model the non-Schmidt effects by assuming that the dislocation core itself is a torus of it's an eigenstrain region, an Eshelby inclusion of the form of a donut of a torus, and we can compute the eigenstrain terms or the eigenstrain matrix for this dislocation core using atomistic simulations, using a methodology I'm going to tell you about in a minute. And once we know these eigenstrains, we can predict what are the non-Schmidt effects, and we can compare with brute force atomistic calculations, and it works very well. So you can also model some of the properties of the dislocation core by assuming that you have an eigenstrain, a core eigenstrain. I tried to do something else than dislocations. I always go back to dislocations. So it's been my life since I was your age. And so there's some math involved, but what we are writing here is exactly what I said here, nothing more, nothing less. What is good is that for the dislocation, the assumption that the elastic constants are homogeneous makes sense because it's the same material inside and outside, right? So that in the case of dislocations, that's not the issue. The issue is how you stabilize the core width of the dislocation, and most of the paper is some mathematical tools to try and control the width of the dislocation core. But in the end, you have, okay, there's a lot of things going on. I thought there was, yeah. So for example, here, you start with a loop, which is here, and then, which is modeled by an eigenstrain. And then we did, we minimize the elastic energy using some of the arguments we have written here, and we do dynamics on it, and we see that the loop spontaneously will shrink and disappear. So this is a simple case of dislocation dynamics. And then what we did is, what is nice is once we have the dislocations in place, we can mix. We can have different fields. We can have a field that represents the dislocation, and we can have another field with another eigenstrain that represents a second phase, that represents precipitates. And then we can look at the interaction, the elastic interaction of that dislocation loop with the precipitates within a single framework. And that's what we did with some success, but not huge success. But you see that these elongated precipitates here, they block the dislocation. And so you see that when you apply a stress, the dislocation actually will grow but parallel to the faces until it's long enough that it can go inside the precipitates. Anyway, that was for the historical part. So actually, when you add the energy term to stabilize the interface, you put in a length scale already there. You can choose what value it is, but the width of the interface gives you a length scale. That width becomes is a real length scale expressed in angstroms. Yes. So these the simulations I showed you, actually they are not much bigger than an atomistic simulation. But yeah, that was in 1999 or something. So. But nowadays there are several dislocation dynamics code that are based on the eigenstrain formulation, and with nowadays computers, you can do big simulations with these eigenstrains. Now, what I want to do is I want to extract, for example, the missed volume of a solute atom or of a vacancy from an atomistic simulation. How do I do that? What I do is I take in the end, it's going to be a simulation cell, but I can assume I have a domain, and on the borders of the domain, I apply periodic boundary conditions. So I have a periodic domain in all directions, and etc., P and P. and I assume that the size of the domain is fixed at some length, L here, in the reference configuration, so in the pure matrix. Now initially I have 0 eigenstrains. Now I assume that inside that domain there is a region where now I have a non-zero eigenstrain. And I re-relax the system. So initially I had 0 displacements. It was my reference configuration. I create some eigenstrain somewhere. I relax the system. So now I have a displacement field inside the region. And from the displacement field, I know that I have deformations and I have stresses now everywhere. If I use fixed boundary conditions, what does it mean for? Okay, we can go step by step. If I look at the displacement field, what does it mean? So if this is, for example, this is the beginning of my axis. So I have an axis x here, and I have an axis y here. And for example, I'm looking at the displacement here compared to there. So because of my displacement field, I will have a displacement here, u at 0. And if I'm looking only in one direction, if I'm looking at the u on the other side, L, they have to be the same, right? If it's periodic. So I have UL minus U0, which is 0. But this difference, I can rewrite it as integral between 0 and L of du over dx, which is 0. So it's not an exact, so this is related to what? This du over dx. This is the strain. So this would be epsilon xx, for example, right? Because if I'm looking at the displacement in one direction, in the direction x, this would be integral from 0 to L of epsilon xx dx, which is equal to 0. If I put a 1 over L before it, what is this? 1 over L, the integral of epsilon dx. That's the, sorry? It's the average strain. So this means that the average of epsilon xx is equal to 0. Right? So this was just, so we can do a much better calculation. It's a bit more involved. But what we can show is if we have fixed periodic boundary conditions, so fixed periodic boundary conditions, that implies that the average of any of the components of the stress tensor, of the strain tensor, so this would be, we can generalize in 3D, so it's 1 over V, the integral over the volume of epsilon ij of R dV. This is 0. Okay? Now, what about the average stress tensor? So same expression, 1 over V, integral over V of sigma ij of R dV. By definition of the stress, what is sigma ij? It's aCijkl multiplied by strain, yes, and then strain minus the eigenstrain, right? It's epsilon ij, epsilon kl minus epsilon kl star dv, and sum over k and l, right? Now I can separate. That gives me 1 over v, integral over v Cij kl epsilon kl dv minus 1 over v, integral over v Cij kl epsilon star kl dv. Now, when we model these defects, what we are usually assume is that the defect has a certain volume, say V0, V0, and the eigenstrain inside the defect is constant. So my eigenstrain is either equal to epsilon, like with what we have done here. So it's either equal to a constant inside the defect of volume V0, or it is 0 outside. So what happens to this equation here? So this first term here, what is it equal to? It is equal to 0, are you sure? Yeah, it is 0 because, so this is a constant, so I can take it out. And I have a 1 over v, so I have aCijkl, and then I have a 1 over v integral over v epsilon kl dv. This is nothing but the average of epsilon kl, and this is 0 because of the fixed boundary conditions. This goes away. And now this term, what is it equal to? So epsilon kl here, star, will be non-zero only inside the precipitate, where it is constant. So the integral will give you directly, so you have, there's a minus, there's aCijkl, exactly, epsilon star kl, v0 over v. Yes? Now I can invert that. So this is the stiffness matrix. I can invert it, the compliance matrix, because this is a matrix product, right? So I can, if I invert that, I directly get epsilon kl star, which is equal to minus v over v naught, Sijkl sigma kl. So what do? Atomistically, I take a simulation cell, fixed by periodic boundary conditions. I create a defect. And then this average stress tensor, this is just the virial stress tensor that LAMMPS gives you. It's the overall stress tensor inside the simulation cell. So I read the stress tensor, the pressure tensor inside my cell from LAMMPS. Then I use the compliance matrix, multiply by, so this volume here I have to assume it's given. And actually the result that I have, so what is really constant is V0 times epsilon star. If I change V0, I change the value, but what does not change is V0 times epsilon star. But so if I say, for example, if this is a vacancy, this would be like an atomic volume. And I have the volume of my cell, and that gives me this value. Now, if I want to make sure that what I'm doing is not crap, what I need to do is I need to do this calculation for different volumes and make sure that I get the same value here. If the value that I get here depends on the volume, then I know I cannot model my defect by using elasticity. But if it converges, if the simulation cell is big enough and I see that the value that I get here converges to a constant value, it means that what I'm doing makes sense. This will be given by LAMMPS. This will depend on the atomic, the elastic constants. This will depend on my simulation cell, but this is something that I choose. So actually what is really given by the simulation so this term here is a constant. It's something which is given by the elasticity. V0, I can choose its value. If I change the value of V0, I will change the value of epsilon star, but such that the product of the two will remain constant. Yeah, but so in this, in the elastic framework, it does. So the bigger the volume, the smaller the equivalent eigenstrain I will have inside my object. It's, yeah. as I said. So it's what is really well defined in that framework is the product of V naught times this. And this is equivalent of, it's an activation volume actually, to use words connected to other fields. This is an activation volume. Okay, that works. Now this, if I'm using isotropic elasticity, actually this expression here is very simple because what's Hooke's law with in isotropic elasticity? What does Hooke's law tells me? It tells me that sigma is equal to say it again? It's a little bit more involved because we have these two elastic constants. So yesterday we wrote that generalized. So if I'm talking in terms of matrices, I need to use the generalized Hooke's law. And yesterday we wrote it down, and it's, what does it look like? You can look at your notes, or it's E divided by 1 plus nu. Yes, so that's Hooke's law. And basically, I mean, the Cij-KL matrix is hidden in this sum, right? What I need is actually, I need to invert that relation so that if I know sigma, I can get epsilon, right? And to invert, it's very simple. I take the trace of that expression. So if I take the trace of that, so the trace of that matrix, that gives me what? That gives me E over 1 plus nu. And then that would be the trace of epsilon. Now I have plus nu 1 minus 2 nu. And the trace of this is 3 times the trace of epsilon. Yes, so I can take epsilon, trace of epsilon out. And then I have E over 1 plus nu. And then I have 1 here. So I have 1 minus 2 nu plus nu divided by 1 minus 2 nu. Thank you. So that's going to be 1 plus nu, which simplifies with this one. So what I get is E over 1 minus 2 nu, trace of epsilon. Yes? And now here, what I do is I simply say that epsilon here is equal to 1 plus nu over E times the sigma. Right? I take this term and I put it on the other side. So 1 plus nu over E times sigma minus nu over 1 minus 2 nu. And I have trace of epsilon, but trace of epsilon is 1 minus 2 nu over E. This is weird. Trace of sigma. And then I have identity. Well, maybe it's correct. I'm not sure. I had forgotten it. I didn't know it. I had forgotten it cancels. Anyway, let's assume it's correct. And you see here, so this now I could take E out, but it's the same shape. You see that I have epsilon, which is a function of sigma and trace of sigma. So from LAMS, I know the sigma matrix. I take its trace, blah blah. I do this, and then I get the epsilon star of my defect. We're not going to do the calculation. I mean, we could do the calculation. It takes. So this is just the same as what we've done. So what I did in this example, I took so exactly the same FCC crystal as you have been playing with, the same aluminum potential. And then I remove one atom to create a vacancy. I minimize the energy with fixed boundary conditions, and it's in red because otherwise the calculation doesn't work. I compute the average stress tensor, and then I use the relation that we wrote here to get the eigenstrain tensor of the vacancy. So the result of LAMPS is given here. So this is for different, so 4, 8, 12 is for different cell sizes. I get here the stress tensor from LAMPS, and I apply this formula using, so you need to know beforehand what is the shear modulus and Poisson's ratio for your system. So this was computed for the potential, 25.5 for nu and for mu, and 0.34 for nu. I apply this, and what I get is, so I'm not sure if, yeah, so this is the, so as expected for the vacancy, the eigenstrain tensor is a diagonal matrix, so all three elements are the same, and this is showing one of the elements as a function of the size of the cell, so 4, 8, and 12. And you see that the value varies from minus 0.147 to minus 0.1456. So it's a small variation, and clearly it's converging to a given value. So it means that so I should be doing more, even bigger to have a precise value of the eigenstrain. But basically, it tells me that the eigenstrain of the value of the vacancy is minus 0.145. And so it means that the vacancy corresponds to, it's as if it was a small solute, which is only 15% smaller than the atoms in the matrix. That works? I can do the same for an interstitial. It forms you don't see, but there's a dumbbell here in the middle, here and there. This is the dumbbell it's these two atoms that share the atomic position in between. So this is the dumbbell. You do exactly the same thing. Then you get the eigenstrain tensor, but this is the eigenstrain tensor in the cubic frame of reference, whereas the dumbbell is aligned along a 1-1-1 direction. So you have terms everywhere. You have terms along the diagonal, but also outside of the diagonal. But if you diagonalize this matrix to find the principal components, you see that indeed there's one eigenvector along the dumbbell, along the 1-1-1 direction, and the eigenvalue is 3.23. And then there are two other eigenvectors that are perpendicular to that direction with the same value, and it's negative of 0.438. So you have a very large elongation along the 1-1-1 direction and a sort of a Poisson contraction in the x and y directions of this value. These numbers obviously will depend on the potential, the system, the blah, blah, right?